which tell us something about how the first generation of supermassive black holes came to be, and also how their host galaxies grew to catch up with their fast growth. Now, we've already heard a lot about how black holes destroy galaxy evolution and all the problems they cause to your galaxies. But looking at this picture, we also realize supermassive black holes have feelings too, and they have their own issues to solve. Specifically, focusing on the very high redshift universe, which I mean redshifts 5 and beyond, we ask ourselves, how do the first generation of supermassive black holes came to be? How could they form so early? How could they grow to be so massive? That's exceeding 10 to the 9 solar masses, less than 1 billion years after the Big Bang. And in the last years, we've heard a lot of activity about massive seed, black hole seed formation, suggesting us very different and sometimes exotic models for massive seed creation, with seed black holes going all the way up to 10 to the 6 solar masses or so. But as you can see from this plot, even with these optimistic and sometimes even contrived models, we still have a long way to go if we want to explain the first generation of supermassive black holes observed in quasars. And this long way has to do with how you grow these black holes. And just to illustrate how problematic this still is, I draw here 3 very simplistic exponential growth tracks for a black hole which is observed as a quasar at redshift 5, the kind of object that I will discuss throughout my talk. And you can see here that unless you grow your black hole very efficiently, so you either accrete at the Eddington limit 100% of the time, or whether you accrete at 10% of the Eddington limit and or only 10% of the time, has a huge impact. In other words, it's either you don't need any of these fancy seed black hole models, or they don't help you at all. So again, just to stress, there is still a lot to be said and learned about what drives early black hole growth and not just their creation. If you want to think about it mathematically, the seed black holes only give you the 0 point of the exponential, while the other parameters, of course, determine the e-folding timescale. And so to grow the black holes, we have to feed them constantly with cold gas, and we have to make sure that they accrete at high accretion rates, close to the Eddington ratio. How do we do that? We have several scenarios in mind. One of them, of course, the famous merger-driven scenario, where galaxies merge through equal mass kind of encounters. This can drive a lot of star formation and also a lot of black hole growth. We already mentioned this throughout the day. I will only mention that, as AGN people, we tend to select things only in this subset of, only these phases of any merger, and usually it's pretty hard to identify AGN in the heavily obscured phase. But this is definitely not the only way to grow black holes in their host galaxies. We also heard about other scenarios. First of all, violent disk instabilities in gas-rich galaxies can drive a lot of gas to the centers of the black hole, to the centers of the galaxies, and kind of expedite some of the growth. And this can actually be very efficient at high redshifts, because galaxies are, again, have more gas in them. And also, this can be made even more efficient if you consider larger scale streams of gas from halo scales and beyond. But this requires very high densities, or this requires that the black holes are located in significant overdensities in the early universe. And again, there are many simulations that show this. One particular example is work done by Thiago Costa here, where it shows, and Martin, I think you're also there, where it shows that actually it's pretty hard to create supermassive black holes if you start from your average density piece of the universe. But if you if you switch instead to an overdensity, And this one isn't then. Wow. Okay, so as I said, we can use the carbon-2 line to get estimates of the dynamical masses of all the quasar hosts. And what we learn from this is that most of them are already consistent, kind of consistent with the local relation between black hole mass and galaxy mass. Now, this comes with huge caveats, both to the determination of the dynamical masses themselves, and then, of course, our usage of these dynamical masses as kind of probes of the total host galaxy mass. But it is consistent also with other results of redshift 6 quasars. And again, you can see that the black holes are slightly overmassive, slightly above maybe the local relation, but this might have to do more with biases than with a real trend. But by far the most interesting thing we found in our ALMA data is that these black holes do not reside in empty spaces, but actually are accompanied by interacting, what we think are interacting galaxies. You can see in this example, an interacting sub-millimeter galaxy separated by less than 50 kiloparsecs. If you take the dynamical masses I just mentioned, this is consistent with a major merger, which is just starting now. And actually we find this kind of companions for 50% of our quasars, which is much, much higher than what you see for normal star-forming galaxies and also from other reference samples. These are the few examples. Most of the separations are, sorry, in 2 cases, we have separations of 50 kpc. Sometimes it's much less than that. We have another blob here, which doesn't have carbon-2 emissions, so we're not really sure what's going on. But this is definitely suggestive of high overdensities in the surroundings of these fast-growing supermassive black holes. This is, again, consistent with new results coming out from another sample of high redshift quasars. This is work published a month ago or so in Nature by the Carly and the collaborators in MPIA. They were looking at a much larger sample, found only 4 companions, so the fraction of overdense regions is lower, but this is still significant overdensities in the early universe. Within our small sample, we also have some surprises. Not everything can be explained just by overdensities or merging systems. For example, this system, which is completely isolated in the sense that it has no close companions. It has a crazy high star formation rates of thousands of solar masses per year, if you trust the sub-millimeter calibrations. Completely isolated, as I said, and it does look like a very thick rotating disk, while still hosting a very luminous quasar, which is somehow not hidden and not obscured by this huge amount of dust. So again, some things here are just mysterious and we don't understand. And one way forward is, of course, to increase the sample size. And this is what we're doing right now. Within ALMA cycle 4, we got time to increase sample size up to almost 20 sources. We have other follow-up campaigns, including freshly approved HST time to probe, larger scale separations to confront simulations more directly, and also try to look for dual AGN activity in the X-rays. So I'll just post my summary. First of all, I try to convince you we have now a large and still growing sample of high redshift, fast-growing supermassive black holes that can teach us something about the early phases of black hole activity, perhaps AGN feedback, and galaxy formation and evolution. With ALMA, we're now finally capable to resolve small scales within the host galaxies, both in dynamics of the ISM, and also covering the large scales required to probe the environments. We see a very high fraction of overdense regions, 50%, maybe even more, if you think that they're all in advanced mergers, the high star formation ones. And one crucial point that I forgot to mention is that none of these companions was seen in our Spitzer data. So this tells you something about the previous attempts to see overdense regions in the early universe. You really need instruments like ALMA or other sub-millimeter facilities because it's all dust rich, gas rich and dust rich. As I showed you, we still have many open questions with our sample, also with other samples. Some systems just don't make sense. I don't know how to how to drive 3,000 solar masses per year in star formation rate without a merger, and it doesn't seem to look like a merger, the one example I showed you. We have other open questions here. For example, we don't see any sign of AGN feedback, right? These supermassive black holes have been growing continuously since redshift 20, but didn't affect the host galaxy. And I tried to show you that we have a bunch of follow-up observations that we're planning to do. So thank you.
Question over here.
Right, so this plot tries to illustrate this. This is back to the Herschel data. What you have here is our precious, first of all, the Sloan spectra, the precious VLT time over here, and then you have the worst case scenario for what the AGN can do with the warm AGN dust. And you can see that even the Herschel bands probe a regime where you're safely free of any AGN contamination. The new ALMA points are down here, actually, when you don't have to worry at all, I would say. That's a fair point. This is why I said that it could be that even the systems which don't have companions are in an advanced merger stage. I would highlight, however, that you see this rotationally supported kinematics here, and this is also true in the crazy example I showed toward the end. You have these very clear velocity gradients, and if you look at the center of light, of the continuum light, it's pretty well centered, sorry. So it's not like two different, you know, reservoirs of gas sloshing each other. Right.
I was wondering, how do you quantify when you see an image like that, whether this is system with just rotating this or going to be a mode? How do you go about trying to quantify that difference?
Right, it's pretty hard. The question was, how do we quantify whether this crazy example was a merger or not? It's pretty hard, and even with ALMA, I have to say we will never go well beyond 1 kpc resolution. So I think we will try to revisit them with higher resolution, but you have to go back to disk models and, you know, just hope that they make sense. In this case, it was pretty thick, so it might end up not being consistent with the disk. Yeah. Right, and the beam size, because we have a lot of smearing. Yeah.